Welcome to the course on superconductivity. I'm Gail Berthet from the Applied Superconductivity Laboratory of Seoul National University. Today we're going to talk about the critical parameters for superconductivity. We will go over the three critical parameters for superconductivity, starting with the critical temperature, Tc, the critical current density, Jc, and the critical magnetic field, Hc. We will first do a small recap of what is superconductivity. Using normal cables made of some conductive material, there is an electric resistance. Therefore, when applying a current, some of the power is dissipated as heat. This power loss, referred as resistive loss, is proportional to the current and the resistivity of the cable. Superconductive materials have a null resistivity, hence, they carry the current without resistive loss. This property makes superconducting materials especially attractive for power application or to make magnets. For instance, on the right-hand side you can see a photo of a superconducting coil. For normal metal, like copper, the resistivity decreases as the temperature gets closer to zero until it reaches a minimum. For superconductive material, the resistivity follows a similar behavior until it reaches a threshold value where the resistivity goes to zero. This value is the critical temperature and is the reason why we need to cool superconductors to use their properties. We will say that a superconductor is in its resistive state or normal state above this value and superconducting state if it is below. In the same way, applying a high current or magnetic field on a superconductive material can drive it to its resistive state. Therefore, we have the three critical parameters for superconductivity: the critical temperature, the critical current density, and the critical magnetic field. On a 3D graph with axis current density, applied field, and temperature, we can draw the critical surface that shows the interdependence of these three parameters. Above this surface, the material is in its normal state and below, it is superconducting. On a side note, the critical temperature is conventionally defined when the superconductor is with no applied magnetic field and no electric current. Also, one could argue that pressure could be a critical parameter for superconductivity, showing as an example lanthanum superhydride being superconducting only at high pressure. However, this parameter's effect is not universal to all superconductor and is different from the other critical parameters. You can see on the right-hand side graphs the critical temperature dependence on pressure for several superconductors. Because of the reasons mentioned before, we will not include it with the main three critical parameters. To conclude, by definition, the critical parameters are the conditions required for a superconductor to be in its superconducting state. These parameters are important because they are key properties of superconductive materials. They will be used for any design involving superconductors. As a side note, conventionally, the critical temperature is defined with no applied field and no current. Also, pressure is usually not referred as a critical parameter.